Today, we're going to dive into the brilliant, and let's be honest, often brutal, trade-offs of rocket science. We're going to try and figure out what actually makes the best rocket. And I think you'll be surprised to learn there's no single right answer. It turns out it's all about this incredible balancing act. So let's just jump right in with the question that I know is going to sound a little weird. What in the world does the legendary guitarist Jimi Hendrix have to do with sending things to space? Well, believe it or not, the answer has everything to do with the single biggest challenge in all of rocketry.
I mean, think about it. You give a total beginner a guitar and 40 hours to practice, they'll go from knowing literally nothing to maybe strumming a few songs. That's a massive, massive improvement, right? But what happens if you give Jimi Hendrix, already at the peak of his powers, another 40 hours of practice? You're going to struggle to hear any difference at all. That right there, that's the law of diminishing returns, and it's the perfect way to understand the single biggest problem in rocketry.
And that brings us to something rocket engineers have a name for: the tyranny of the rocket equation. It's this, brutal catch-22. To go faster or farther, you gotta add more fuel. Simple enough. But that fuel is heavy, so now you need even more fuel just to lift the fuel you just added. It's this vicious cycle that has ruled rocket design for 100 years.
And this is the culprit, right here, the Tsiolkovsky rocket equation, first figured out way back in 1903. Now don't worry, we're not going to break out the calculators. All you need to know is that it boils everything down to three key things: delta V, which is just the total change in speed a rocket can pull off; ISP, which is basically the engine's efficiency, its oomph; and then there's the mass ratio. And that's just a fancy way of saying how much of your rocket is gas versus how much is the actual ship and the stuff you're trying to get into space.
Okay, so check this out. This is where that tyranny gets really, really real. Imagine you're an engineer and you need to add just 1 little kilogram to your satellite. Just one. Well, to push that extra kilogram to orbit, your upper stage now needs, let's say, 10 kilograms of extra fuel and structure. But wait, it gets worse, because now the first stage has to lift all of that, which means it needs to pack on something like 100 kilograms of extra mass. It's wild. One tiny little change way up at the top creates this huge cascading problem all the way down at the bottom.
So for, decades, that was the entire game, fighting that cascade. But then, companies like SpaceX came along and threw a massive plot twist into the story: reusability. Because trying to land a rocket after you launch it, well, that just throws a whole new wrench into this crazy balancing act.
Yeah, it turns out reusability and the rocket equation are not friends. They fight each other. Think about it. To land, you have to keep a bunch of fuel in the tank for the trip back home. Plus, you've got to bolt on all this heavy hardware: landing legs, grid fins, you name it. And from the cold, hard perspective of just getting to orbit, all that stuff is dead weight. It does nothing to help you go up.
So take a look at how this breaks down. See, for a normal rocket, you've got your tanks, your frame, but on a reusable one, you've got this whole extra chunk of mass for things like landing gear. And all that stuff, the legs, the fins, the landing fuel, it has to be hauled all the way up into the sky, which just makes that tyranny of the rocket equation even more tyrannical.
Okay, so with this new complication, a huge question pops up. If you're going to build a modern, reusable rocket from scratch, what's the best fuel to put in the tank? Well, luckily for us, a massive new research paper set out to answer that exact question, running thousands and thousands of simulations to find the perfect design.
The study zeroed in on the big three, the main contenders for rocket fuel. They all use liquid oxygen, or LOX, as the oxidizer, but the fuel part is different. You've got liquid hydrogen, super efficient, but man, it takes up a ton of space. Then you've got your classic kerosene, or RP1. It's dense, packs a punch, but it's not as efficient. And then there's methane, which is kind of the new kid on the block, seen as a happy medium between the other two.
And trust me, this choice is a huge deal. Because as you're about to see, what you put in the tank completely transforms the size, the shape, the weight, everything about the rocket.
All right, let's actually look at these designs. Now, look at the hydrogen rockets on the far left of each of these charts. See those purple bars for mass? They're the smallest. These are the lightest rockets, period. But now look at the height. They're absolute skyscrapers. That's because hydrogen is so fluffy, I guess? It's not dense at all, so you need these gigantic, massive tanks to hold enough of it. Now slide your eyes over to the RP1 rockets. They're way shorter, much more compact, but their mass bars are a lot bigger. They're seriously heavy. And this trade-off brings us right to the heart of the whole study. Because to find the best or optimal rocket, you first have to define what best even means. Best at what, exactly? Are we talking about the lightest rocket off the pad, the cheapest one to fly, the one with the least waste?
You see, the answer totally depends on the question you ask. So the researchers were smart. They defined 3 totally different goals, 3 different ways to win. First up, minimizing gross liftoff weight, or GLO. That's easy. Just make the whole thing as light as possible on the launch pad. Second goal, minimize the structural mass, so the lightest empty rocket you can build without any fuel. And the third goal, and this is a really important one, minimize the expendable mass. That's the part you throw away every time you fly. And that's a really good stand-in for cost.
All right, so we've got our fuels, we've got our goals. The simulations are run. Who's the winner?
Okay, let's look at goal number 1. If all you care about is having the lightest possible rocket sitting on the launch pad, who wins? And it's not even close. The winner, by a long shot, is liquid hydrogen. For this specific mission to a high orbit, that incredible ISP, that oomph we talked about, means a hydrogen rocket is just way, way lighter at liftoff than anything running on methane or kerosene.
But here's the thing, lightness isn't everything, right? Especially now with reusable rockets. So let's switch it up. Let's chase a different goal. What if we want the cheapest rocket per flight? And like we said, the best way to measure that is by looking at how much mass you have to throw away each time, that expendable upper stage.
And get this, the results completely flip on their head. For the exact same mission, the dense fuels, kerosene and methane, are now the winners. So why? It's because that high density lets you build a much smaller, lighter, and therefore cheaper upper stage. And since that's the bit you're ditching every time, a smaller throwaway part means a cheaper flight. Simple as that.
So this complete reversal from one goal to the next points to one of the biggest takeaways from this entire study. It turns out the best design fundamentally changes based on one simple question. How many times are you going to reuse it? And this graph shows it perfectly. You see that line going up? As the number of times you plan to reuse the rocket increases, the smart move is to make your first stage bigger and more powerful. You give it more of the total delta V. Basically, it makes financial sense to invest in a beefier first stage if you know you're going to fly it over and over and over again because you spread that cost out.
So, let's bring this all back to reality. For something like the old Saturn V, an expendable rocket, the goal was pure performance. Get to the moon no matter what. So, high-efficiency hydrogen for the upper stages made perfect sense. But for a workhorse like the Falcon 9, where the goal is minimum cost per flight, everything changes. Suddenly, a high-density fuel like kerosene is the winner because it helps you shrink the part you have to throw away.
And that's really the punchline to this whole story. There is no single best rocket. There's no magic fuel. The optimal rocket is always, and I mean always, this brilliant, difficult compromise. It's a balancing act between competing needs, and the right choice depends completely on what game you're trying to win.
Which leaves us with a final big question to think about. The tyranny of the rocket equation was the big monster to slay for the first century of spaceflight. You could say reusability is the big challenge for this century. But as we start seriously looking at Mars and beyond, what's the next great tyranny? What's the next impossible problem that rocket science is going to have to solve?